Welcome everybody, Sheldon here with Data Systems Architecture, and this is the fourth video in our Advanced Architectural Concepts and Principles playlist, and we're going to be getting more philosophical once again, but talking about something very technical, which is our considerations when we think about throughput and latency in our data pipelines. So, engineers who don't do a lot of data engineering work often confuse the terminology throughput and latency. And throughput is the amount of data transferred over a period of time. So for example, megabytes per second. That's the overall amount of data we've moved over that period of time. Latency is how quickly did we write a single record from our data sink to our data source, so that from our data source to our data sink. So that would be our sink timestamp minus our source timestamp. For example, if we are using batch inserts to write data into a ClickHouse database, this is going to be optimized for throughput because ClickHouse is designed to have large tables and support large aggregate queries. You generally don't use it unless you were ingesting a lot of data all at once all the time and adding a lot of rows. And so ClickHouse is designed to optimize for throughput rather than latency. If you try and write one record at a time into ClickHouse, like a few milliseconds apart, it's going to take the cluster down. It does not do that well. As opposed to a database like AWS TimeStream, which is very much optimized for latency, where it is very much designed for you to send records one at a time, very frequently, and it will handle things under the hood to make sure that the right operations are very efficient. And the reason why these kinds of trade-offs exist is due to the underlying implementation of the database technology itself. And this will always have trade-offs in terms of read optimization versus write optimization. And so the trade-offs for latency versus throughput are sort of related to the purpose and needs of your data and your data sink. Redundancy in your data pipelines can also cause latency issues. For example, if we're using a decoupled data pipeline with a distributed messaging system, such as Apache Pulsar or Kafka or RabbitMQ, and we have configured our topic so that it has replicas, it has many replicas across the cluster, those write operations will take time. And that data will not be available to the consumers to write to your data sink until all of the replication has been completed. And so it may be faster to just have Kafka store that data in memory on a single node. In fact, it will be faster without any redundancy. And this will lower the overall latency of your system at the price of reducing the redundancy and overall resiliency. Another trade-off is the problem of message ordering guarantees. So let's say that you have a downstream data sink where you need to ensure that you read all of the records from your source in order and you write all of your records to your sink in order. As soon as you start to optimize for latency or throughput, you may be making it impossible to maintain the order of your messages for various reasons. Finally, let's discuss the trade-offs with deduplication. Oftentimes, there's a risk that in our pipelines, we end up writing records more than once to our data sinks. And this is due to a number of factors. It could even be that there are duplicate records in our data source. We may not have control over that. However, in a modern distributed messaging system like Apache Pulsar, we can actually configure our topics to deduplicate data in flight so that there is no risk that we're going to be writing duplicate records, assuming that we are implementing our code correctly. However, the only way that deduplication can work effectively is by maintaining a copy of the data inside of the topic, and having a long certain retention time for that data, because as events are written into the topic, when a new event comes in, it will check to see if that event is already there before it adds it to the topic, and that's how deduplication works. But if you are aging off your data off the topic too quickly, then you are going to potentially age off data before your duplicate data comes in. And so this is also related to the ordering of data and deduplication. When you start working with those levels, that level of detail, just be aware there's going to be trade-offs, and that facilitating deduplication is probably going to incur latency. Another example of that, Postgres, upserts in Postgres. If you're on a team and you don't know if you were adding new records, you're updating existing records, when you're doing inserts and you use the upsert statement, Postgres will have to do a full table scan for every record that you're writing to see if the record already exists. And yeah, I can use indexes to optimize that, but that query is going to take time. Whereas if you were just writing the data without checking for an existing record, that's going to be much faster. So these are all trade-offs. Let's talk about data localization and hardware concerns. So I've ordered this list in terms of the fastest, highest performance to slowest, lowest performance at the bottom. Now, if our data is in flight, then our data has to be somewhere on our cloud or our data center or whatever. That copy process, the more copies we make, the lower our latency, the higher our latency is going to be. So if we make one copy and we store in memory inside of a single application in our data pipeline, this is going to be the fastest way to move data from data source to data sink. If we also write that data to a local disk to have one replica of the data in our pipeline, that is the next fastest thing we can do. The third fastest thing would be to start distributing or having multiple replicas of the data across multiple hardware machines, physical machines on the single rack inside of the data center, because the networking is closely interlinked. The transfer speed will be very fast compared to replicating on another rack in the data center, which would be number 4, versus replicating across multiple data centers and then having to go across a huge network and incurring more network latency on that side. So in general, the higher level of resiliency that we have on the cloud side for our data that's in flight, the higher our latency is going to be. In general, latency ain't it. Latency is usually not what teams actually care about. What teams will actually care about is throughput. We want to know how fast can we transfer records, not how quickly can I copy one record from one place or another. And there are exceptions like high frequency trading and things like that. But in general, we have a lot of data in one place and I don't want to wait. I need that my developers are waiting, and I need to optimize for throughput so they can start working with a new copy of the data in this new database that we've set up. You need to think about defining tolerances for how much data you're willing to drop if you're building a low latency system. It may be that it is more efficient to not worry if you're missing a relatively small percentage of records in your pipeline. There will be other aspects of data integrity to consider, and maybe the overall integrity of your data is not as important as moving it quickly, and that can give you a speed advantage in some scenarios, but that's very case by case. If you're consuming data from a third party, you need to figure out how slow their system is, because if you spend a lot of time and engineering effort optimizing for fast writes but you're getting data from somebody who's already really slow, then that time is wasted. If you are dealing with fetching data from across the internet, different third-party providers, or different cloud databases, or like whatever it is, you're going to be making a lot of network hops over the entire internet, and that's going to incur latency, obviously. So it's important to understand, the network topology of what you're working with. Your database provider may be able to set your database up in the same availability zone or same data center as your data pipeline code and as maybe your source data. That can speed things up. So understanding the network topology of your data system is really important for optimizing, honestly, both throughput and latency, but especially latency. And one thing that I've noticed is if you're building a low latency system and you're working with a vendor or a cloud provider who's really advertising like, hey, this is low latency, super fast, blah, 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 the only way you're going to get the maximum speed out of their system is if you really go all in and you use all of their stuff. So a good example of that would be like AWS TimeStream, which I think is super cool. But if you are copying data out of Google Cloud and writing it to TimeStream, that's going to incur a lot of network hops along the way, and it's going to slow everything down. Whereas maybe if you were loading data out of Amazon S3, there's some optimizations that the cloud provider may facilitate to make those writes really, really fast because you're all in with their tech and that's what they want, right? So just in general, plan on going all in with one provider if you're optimizing for low latency. And finally, if you utilize a modern data warehouse architecture, then you can facilitate long-term resiliency and low latency simultaneously by having multiple pipelines that work with the same data. So you can, there's a video in our data architecture types series about the modern data warehouse for a better description, but very briefly, let's say that we have a data lake where we have long-term storage of all of our raw data that is well replicated and backed up and all that kind of stuff. Your data pipeline can write there. That write can take all the time in the world. And then you can have an adjacent data pipeline that writes to your real-time streaming database or whatever and doesn't deal with the data lake at all. And if you've decoupled your pipelines, then you can set something like this up. So this is why modern data warehouse architecture is real nice. Please be sure to review the other videos in the series to gain more knowledge about advanced architecture for data systems, and I will see you in another video.